On Friday, we talked about the definitions of polynomials. We talked about some important words to know, and that was about classifying polynomials. So, can anybody tell me the example you wrote down for number 1, a quartic polynomial? Anybody? Quartic polynomial. Does anybody know what quartic means? Okay, that's it.
To the fourth power minus x squared minus 11x minus 11. Right, that's it.
This is a quartic polynomial. Very good. And we know it's quartic because it's fourth degree, and fourth degree means quartic. So, a degree is the highest exponent listed.
Wait, what does quartic mean?
So like if x to the third was here, we would call it cubic. If it was x to the fifth, we'd call it quintic.
What about x to the second?
Quadratic. They should have called that one like binomial or something, but they went with quadratic. A lot of people think quad means 4, and it does. But the area of a 4-sided figure is a side squared. So when something's squared, we call it quadratic. Students like to argue that quad word, but side times side squared is quadratic. Fourth degree, and so degree, I just want to remind you of this vocabulary word, is the highest power in a polynomial. And in standard form, it needs to go descending exponent. So this went 4, and then 2, and then 1, and then a constant. That's good. The other word we talked about was leading coefficient. And the leading coefficient here is the 1 out in front. It's invisible, but it's right there. And then you're going to write an example of a polynomial that is not, or something that is not a polynomial.
There you go.
That's what means.
Who got one that's not a polynomial? Ellington, did you do one that's not?
No, that's.
Does anybody remember the rules that we talked about for what is considered a not polynomial? Yes, good. Negative exponent. So here's an example of not a polynomial. Would be like x to the negative third plus 4x squared plus 11x minus 8 equals what? Not a polynomial. Polynomials don't have negative exponents. So this is something else. This has different patterns and rules. We don't apply polynomial rules to this. X plus 4 is a polynomial. I'll show you one that's not. Another example that's not would be 4 over x. X cannot be in denominators. Not a polynomial. Another one that's considered not is a variable x with a fraction exponent. Now we do a whole chapter working on fraction exponents. Fraction exponents are real things, but they're not polynomials. Okay? Any questions on reviewing information from Friday? Okay, let's look at the assignment then from Friday. Alright, so as you're looking through labeled no, not polynomials. And this is the assignment from Friday. You weren't here to see it.
Was it on Khan Academy?
What?
Was it on Khan Academy?
No.
What?
Where did you check for the assignment?
On Khan Academy.
No, but it wasn't there. So where else did you check?
Great idea.
And it wasn't there, so where else did you check?
Where?
On the assignment sheet.
There is no assignment.
There's always an assignment sheet.
Where?
In every folder. On Schoology, every monthly folder is an assignment
Chapter 4 assignment. Oh,
shoot.
sheet. Been there all year, been updated all year.
Yeah, we know just. Yeah, well, I got you this one too. Wow. I was too busy doing this and because I did nothing else. I never ripped it out because I was no way, he gets a free pass. I took a test. That's so rude.
Over here. Okay, if you did not get the book pages on Friday, here they are. Here's the pages if you want to rip them out. Here's the answers. If you don't, you are allowed to keep it. It's not as heavy as if you started the year, so still kind of heavy.
Oh, I thought it said 8:30. They should have given it, but like,
it's okay, it's okay. Stop.
Yo, you touched my black.
Bro, oh, welder.
Alright, here's the answers to the last three. Get out a calculator right now and try it. You have to use your parentheses correctly. You're plugging in this number for all of these x's, and if you don't use parentheses, it'll come out wrong. So, try. This is your chance to correct this right now. Yes, use this button on that calculator.
Wait, is this the page 311, 9 through 11?
It's on the left side. Okay. And for all the other calculators who don't have
don't have a page 311.
Can it? The new pages are right there.
Where?
The numbers are listed on the whiteboard.
Where you talking about? That?
No, just next to it.
That?
Yeah.
No. Shut up. That's literally not it. Wait, where's the
The white basket over there. So Kenny, if you want to keep the book, you can, or you can rip out. It's up to you.
I'll rip it out.
Yeah, the plug-in ones don't go anymore, Blake. So I'll just do the manual. This is how it's functions. And then the thing wrong with this is that the degree is 4. You don't get to light it
This is enough. Miss, how am I supposed to rip this out? This is a giant chunk of.
Just keep it there.
No. Liam, can you give me a quick?
How's the calculator working? It works? Okay. One thing that's happening is that this has to be the subtraction sign, not the negative sign. So if you put the negative sign in next to the 4 in there, it'll come out wrong. It's a different order of operation. The programming is different.
Miss, slow down.
Listen, Kenny, when you're absent, that's lit. That's what people choose to come to school every day.
I didn't see any.
People are tired, they're sick, they've been on vacation, they come here because they hate making work. I get it.
Can we have like a makeup day?
Make them work. Right, when it happens, I'm very flexible. I don't say like you have to do it even if you're
What are you looking at, bro?
you have to ready it the next day. I'm saying, you know what?
There's more homework.
Alright, let's go to chapter 4.2. It's not like we can excuse you from the curriculum now. If you get credit for the course, you did the curriculum.
Oh my.
Alright, so chapter 4.2 is on adding, subtracting, and multiplying polynomials. You already practiced this in Khan Academy. I'm just going to give you some tips and tricks. So adding and subtracting is just combining like terms. And multiplying is just distribution.
Where's the whole bunch? Yeah.
There's some in that white basket right there. Crash out's one of my favorite new sayings. No, I'm proud of you guys all day long.
Wait, your son taught you what?
Please take that to your desk.
Real quick, what?
I was I think nobody was that much, but it's okay. I mean, it's
Miss, come on, miss. I barely have room on my desk.
Alright, Elena, I've I can use. What is this word? Pascal triangle to expand binomials. So everything here is covered in Algebra 1. Adding is combining like terms. Subtracting, also combining like terms. Ellington, multiplying is just distribution. However, in Algebra 2, we do something like this. This is called a binomial, and they're going to put an exponent on it, and you have to expand it. A lot of people, without practice with a teacher, would think this is x to the 6 and 2 to the 6. Like they could just put the 6 inside of here. That is not the case. You have to write this binomial out 6 times and distribute it correctly. It's very difficult. It's a lot, okay? Now, there are many mathematicians in history who worked on this thing called a triangle that gives us a shortcut to binomial expansion. And the triangle holds many patterns that we see all throughout our natural world and throughout all of our math. So Pascal's triangle is a part of the curriculum. I'm not required to test you on it, but we're required to talk about it. I have tested classes on it in the past, but I won't be this year. So this is called binomial expansion. Out of the whole section, this is the only thing that's really brand new to you. I'm going to just quickly look at these examples. Adding and subtracting polynomials is on 319. They show it two ways. One way is to stack like terms vertically and add down. That's how I show it in Algebra 1. But today I'm just going to rewrite both polynomials in order and combine like terms. Multiplying is a lot of distribution. And here is Mr. Pascal, whom we named Pascal's triangle after, and we're going to go over that at the end of class. Now, right now, instead of doing any gray box problems or any examples, I'm going to jump right into your assignment, and I'm going to do the evens. So this is your assignment today. I'm going to do right now 6, 10, 14, 20, and then end at 35. So we're going to go to 325, and instead of doing any gray box problems or any notes, I'm going straight to these evens. You already did this in Khan Academy, so I'm not going to spend a lot of time on going through examples. I'm jumping right into the problems with you. Really wish I was doing number 2. Well. Yeah, these ones with the black lines, I'm going to do right now. You're required to do them all. I'll tell you. I want you to write down on here and highlight it if you have a highlighter. When you combine like terms, you do not change exponents. That's tricky because in a minute we're gonna multiply, and I'm gonna tell you to add exponents. So right here on this same page, sometimes we change exponents and sometimes you don't. So write this down. When you combine like terms, because you're adding, you do not change exponents. You only add up the numbers in front. You can just leave it there. So this next step is optional to you. When I combine like terms, I kind of just do it in my head and write it down. But for now, I'm going to rewrite this with all the like terms next to each other. So I would have 9x to the 4th and 11x to the 4th. And then there's only one third-degree term. I see a positive 4x squared and a minus 4x squared. I see 7 6x minus 5 6x. And I see a 7 and a -9. So I went ahead and just paired up all of the like terms next to each other. So combining them is more clear. Another thing I like to do, especially if this was a test where I might be a little bit nervous or feel rushed, with this many terms, we can accidentally forget something. So I'm gonna check and make sure I wrote everything down. I'm gonna go through and cross out, make sure I got them all. So yeah, I wrote that. Got that. I got 4x squared. I got 7/6. I wrote 7. I wrote 11. I wrote 9. I wrote 4. And I wrote 5. So I will go through and I will double check, make sure that I actually wrote every term down to start combining. And now when I combine, I'm just adding coefficients, exponents stay the same.
Wait, what would a 3 be?
Cubic.
What is the type? What does that mean?
I'm gonna go ahead and focus on this right now. I'm not gonna at the same time teach you Friday's lesson. But it's all right there. It's on page. The assignment's 311. The page is 309 maybe.
309?
There's a chart 305. There's a chart on 305 that explains all the vocabulary.
Oh, thank you.
And then I have 7, 6 minus 5, 6, which is 2, 6. And 2, 6 is 1/3. So I'm just gonna write 1/3. And here's the sum. The sum is a 4th degree polynomial. Now, Kenny, it's also right here is actually the best place.
So the constant term is the last number?
It's a number without x. But Kenny, I'm just now doing this. Are you gonna ask me about this tomorrow?
No, I understand. I just got this. Probably.
What are you
He
talking
wasn't
about?
talking to you.
I wasn't even talking.
All right.
Maybe it was son.
I'm heading to number 10 next. Any questions on number 6 before I go to number 10? The main thing I want to highlight and emphasize here out loud, I want to write it down and I want to say it out loud, that when you're adding, you do not change exponents. Let's go to number 10. For subtraction, it's all the same, but just like we did with complex numbers, when you subtract, you need to distribute -1 to the right expression. So I'm going to multiply this -1 through here and rewrite it. So this isn't any real difference except when I subtract. I'm going to multiply -1 and then combine like terms. Just like with complex numbers, but this is so many terms. So here we go.
Yes.
Hush.
Okay.
What?
You didn't say anything, did you?
Did
you? Did you say Kenneth just now?
You're such a liar. You said,
Oh, in the silence, did you say that?
he's a liar.
It was somebody else? Who said it?
It must have been Blaze.
Blaze, come on. Alright, so you wrote everything with opposite signs, and now I'm gonna do what I just did. I'm gonna put everything in order. There's only one 3rd degree term. Something's not right here. Oh. Squared. Oh, I know it's not right. I messed this up. You guys, I messed something up. If you were copying me, I had a mistake. This was to the 5th, and I wrote it squared just now. Here we go. I'm trying again. Not gonna give up.
Wait, can a polynomial have a square root?
No. Well, it can, but x can't be in there.
So if x is in there, it's not a polynomial.
Roman, did you do 10 yet? Did anybody do 10 yet that can verify my answer?
Yes.
Thank you. Thank you. Thank you. So this is our difference. No. This is what we did on Khan Academy though. The lower is what we did on Friday. Alright, 10 done. I'm gonna head over to number 14 then. Okay, 14 is distribution. So this is find the product. Product indicates multiplication. When you multiply, you add exponents. So on the first two sections, I said don't change exponents. But now that we did some multiplication, I'm saying do change exponents. There are some properties of exponents that you have practiced before. And one of them is called the product property. When you do x squared times x to the third, you're supposed to add those up to get x to the fifth. Which is pretty logical because this would be x times x times x times x times x, which all together makes 5 total x's. So when you multiply, you add the exponents.
Wait, what is the one? Quartic?
So here we go. On 14, we're doing distribution, and that's going to require changing exponents. So that's negative 4x to the fifth times 11x to the third. It's negative 4x to the fifth times 2x squared. It's negative 4x to the fifth times 9x to the first. I do have a little bit of a recommendation here. This x doesn't have an exponent, but it's the invisible 1. So when I have to do all of this, I go ahead and I write 1 in so that I'm sure to add it. Because students will make mistakes in when they do x to the fifth times x to the first, they'll just write x to the fifth instead of making it x to the sixth. So this will be negative 44x to the 8th minus 8x to the 7th minus 36x to the 6th minus 4x to the 5th. Liz, you check in here. We got an assignment. We got an assignment question. I'm finishing up right now. This is the one I would assume people would mess up is this 6. So when you do the odd question, I'm going to question when x is to the first power if you're going to get that distribution right. There's number 14 done.
Thank you.
Does he multiply it?
Number 14, what?
Because negative 4 is negative, right?
Times positive 9.
325 and number 14.
Because you're special. You thought the 4 was a 5.
Oh.
Kenny, I know you're not talking.
Sorry.
Yeah, you must have done 5 times 9.
Yeah, shut up.
Yeah, so that's a good summary. Multiply the coefficients, the numbers in front, add the exponents. You summarized that up pretty well. Any questions on 14? What's the next one I have up here?
20.
20. Alright, 20. 20 is a doozy.
Okay.
It's a trinomial times a trinomial. So it's just you have to distribute 3 times. So one strategy is just to cover up to distribute the 4x squared to everything. And then you cover up the 4 and the negative 2 and distribute the negative 8. And then you cover up the first 2 and distribute the negative 2. So it's a triple distribution.
I mean, what is lobster?
Well, it very well could be, but I'm going to show the Punnett square. But if you go to lobster claw, that sounds right.
What is lobster claw? Is that
I can
right?
picture a lobster claw. Okay, but first I'm going to do the Punnett square style. More and more, and I didn't do this when I was in school, but I'm seeing students love doing the Punnett square. So if I have to do a 3 by 3, I'll make a box of 3 columns and 3 rows, and I'll put the first one on the left side, 4x squared minus 8x minus 2, and I put the second one along the top, and then you just multiply each little bit, and at the end write it out. It's up to you how you want to do it, and honestly, you don't have to show a whole lot. You can just multiply and write it down. So here we go. 4x squared times x to the 4th would be 4x to the 6th. 4x squared times 3x squared, 6x to the 4th. I am going to go ahead and write in an invisible 1 here. And an invisible 1 here, so I'm sure to add that in. That's really the only place I see students in this class make mistakes is with the invisible 1. So this would be 16x to the 3rd. Whoa. And there they all are. I did all that multiplication. Now when I take it out of that square, I'm gonna do it in descending order, standard form.
Oh, that's easy.
Right. So I'll look at the highest power. That would be that 6th degree term.
What?
And then the 5th degree term. And then I'll put both of the 4 degrees in next to each other.
Miss,
Just stop.
what?
You stop moving your hand around.
I'm trying to.
And then I'll do the 3rd degree terms. And then I'll do the squares. And then lastly would be 8x. So I write it out in order. Highest exponent to lowest exponent. And then I go back to that first question we did. And I combine my terms, which means I add the numbers in front and I don't change exponents.
No. Bro.
And this is the product of the trinomial times the trinomial, the triple distribution. At first I had 9 terms, which is a 3 by 3 result. And then I combined my terms and I got it down to 6. Could have been more though. Could have less actually. I don't think could be more. Do you think that's it? Is it possible that oh. If this was like a 4th degree times a 3rd degree, how many possible terms would it have?
Wait, is the Miss?
Why is this answer almost as long as the paper?
You know what?
That's funny.
Any questions on this one?
No.
Trinomial times trinomial.
I understand it. I don't need to know the square.
Wait, I should start back. What I said was very rude.
I have a mistake, you guys. I've been corrected. You guys correct your work. If you copy I know, but I want to make sure everybody knows what I'm doing. So I'm going to have to do a correction here, guys. I made a mistake. 4 times 3 is 12. Hey. Is that the only one you found? So I have to find that. So this should have been a 12 right here. I got to correct this. So that means 12 minus 2 would be 8. I need 10. You have a 10? Sorry, correction, everybody. So what did we learn from this? We learned if you're doing a 3 by 3, there's a lot of different little places to make mistakes. Take a minute, go back and look at it. Maybe you made a mistake. And also, maybe it's best to not have much distractions going on.
Okay.
That's the last one.
This.
No. Okay. Moving on. What's next? Your final answer needs to go highest exponent to lowest. So just reorder it. Okay. We are gonna now pause and look at Pascal's triangle for a moment. Here it is. This is a shortcut for taking a binomial and raising it to any power, and it's pretty easy to create. I used to test honors algebra students on this, and they would say, "Mix, do I really have to memorize the whole triangle?" I said, "No, nobody memorizes this thing. They create it. This is how you create it. You start with 1, 1, 1. And here's the pattern. You write the 1 out here, and then you add the numbers, and you write the sum in the middle. And then you keep going. 1 and 2 makes 3. And then you keep going. 3 and 1 makes 4. 3 and 3 makes 6. 3 and 1 makes 4. And so I used to have a test question, create the first 10 rows of Pascal's triangle. It goes on forever. Can anybody do the next row?
Yes.
Let's hear it.
4 plus 6 is 7. 6 plus 15 is 20. 21. 15 plus 20 is 20. Bro, oh my. Alright.
Yeah.
21. 7.
Question, bro. What I literally asked.
Yeah.
Hey, bro, but it's.
Whoever said you put 21 tracks or 35? Yes, there are repetitions in here. So this holds so many patterns of our natural world. And mathematicians, they just study this all the time. It goes on to infinity. I'll show you a quick video about all the things that are held in this pattern. The concepts actually, for anyone pursuing mathematics, the concept actually.
This may look like a neatly arranged stack of numbers, but it's actually a mathematical treasure trove. Indian mathematicians called it the staircase of Mount Meru. In Iran, it's the Khayyam Triangle, and in China, it's Yang Wei's Triangle. To much of the Western world, it's known as Pascal's Triangle, after French mathematician Blaise Pascal, which seems a bit unfair since he was clearly late to the party, but he still had a lot to contribute. So what is it about this that has so intrigued mathematicians the world over? In short, it's full of patterns and secrets. First and foremost, there's the pattern that generates it. Start with 1 and imagine invisible zeros on either side of it. Add them together in pairs and you'll generate the next row. Now do that again and again. Keep going and you'll wind up with something like this. Though really Pascal's triangle goes on infinitely. Now, each row corresponds to what's called the coefficients of a binomial expansion of the form x plus y raised to the n, where n is the number of the row, and we start counting from 0. So if you make n equal 2 and expand it, you get x squared plus 2xy plus y squared. The coefficients, or numbers in front of the variables, are the same as the numbers in that row of Pascal's triangle. You'll see the same thing with n equals 3, which expands to this. So the triangle is a quick and easy way to look up all of these coefficients. But there's much more. For example, add up the numbers in each row and you'll get successive powers of 2. Or in a given row, treat each number as part of a decimal expansion. In other words, row 2 is 1 times 1 plus 2 times 10 plus 1 times 100. You get 121, which is 11 squared. And take a look at what happens when you do the same thing to row 6. It adds up to 1,771,561, which is 11 to the 6th, and so on. There are also geometric applications. Look at the diagonals. The first two aren't very interesting. All ones, and then the positive integers, also known as natural numbers. But the numbers in the next diagonal are called the triangular numbers, because if you take that many dots, you can stack them into equilateral triangles. The next diagonal has the tetrahedral numbers, because similarly, you can stack that many spheres into tetrahedra. Or how about this? Shade in all of the odd numbers. It doesn't look like much when the triangle's small, but if you add thousands of rows, you get a fractal known as Sierpinski's triangle. This triangle isn't just a mathematical work of art. It's also quite useful, especially when it comes to probability and calculations in the domain of combinatorics. Say you want to have 5 children and would like to know the probability of having your dream family of 3 girls and 2 boys. In the binomial expansion, that corresponds to girl plus boy to the 5th power. So we look at the row 5, where the first number corresponds to 5 girls and the last corresponds to 5 boys. The third number is what we're looking for, 10 out of the sum of all the possibilities in the row. So 10 over 32, or 31.25%. Or if you're randomly picking a 5-player basketball team out of a group of 12 friends, how many possible groups of 5 are there? In combinatoric terms, this problem would be phrased as 12 choose 5, and could be calculated with this formula. Or you could just look at the 6th element of row 12 on the triangle and get your answer. The patterns in Pascal's triangle are a testament to the elegantly interwoven fabric of mathematics, and it's still revealing fresh secrets to this day. For example, mathematicians recently discovered a way to expand it to these kinds of polynomials. What might we find next? Well, that's up to you.
Okay, so Pascal's triangle, like I said, I used to in an honors algebra 2 class. We spent 2 full class periods just diving deep into this, and now it's more like busy work instead of conceptual work. But we can talk more about that